Well, I hope we're all doing doing well, and we'll get started here. Okay, so yeah, next week we have the midterm exam. Okay, there are it's all multiple choice. Okay, so please bring your calculator, pen, pencil, eraser, some kind of photo ID, and your reference tables. Okay, and then I'll provide Scantrons. Okay, it's scheduled for 1 hour 45 minutes. And after the exam, I guess there's like I'll review how the lab will work, because I'm going to assign a lab, and well, I guess class is always optional, but you can stay to see how that how the lab works. Yes, question.
Like a driver's license is fine.
Yeah. Driver's license is perfect. Okay. Okay. Trying to think if anything else needs to be covered there. Oh, you are allowed a one 8.5 by 11 note sheet. Okay. Writing on one side. Okay. Okay. Any questions, or are we good?
Will there be any like practice midterms?
I don't have practice midterms, no. But I don't know, I would say review your lecture notes and the past quiz, this quiz and the other quiz, and yeah.
Confidence intervals for that?
Yes, confidence intervals. So it'll cover up through chapter 6. So today I'll wrap up chapter 6 and I'll start chapter 7, but chapter 7 will not be on the midterm. Okay, so it covers. 6. Okay, so no chapter 7. Okay. Okay, so we we left off in chapter 6. We talked about confidence intervals. Okay, and so the big picture with confidence intervals was this time we start off with a sample. Okay, and then we observe the sample. Okay, and based on so based on what we see in the sample, we wish to say something about the population. So specifically, we observe y bar, and then based on what we see on y bar, we want to say, well, what can we say about the population mean? Okay. And so we said, so basically the idea was, because of the central limit theorem, we said that y bar will generally not stray very far away from the mean mu. Okay, so because of so. So wherever we see y bar, we can be confident that mu is nearby, because we know that y comes from a normal distribution centered at mu. Okay, and then so, for some confidence interval, for some sample, we will say and then I gave you a bunch of incorrect ways to interpret the confidence interval. We said, it's always about the population mean. It's not about anything else. So, and we always say, I'm blank % confident that mu is between this and that. Okay. This week we can expand on this, and we can compare two samples and their respective populations. Okay. So. Okay, and so so in this case, we will have we've got sample 1. And we have sample 2. Okay, and these have each come from their respective populations. And then so from sample 1 we observe y bar 1, and from sample 2 we observe y bar 2. Okay. And chances are, y bar 1 and y bar 2 are probably not going to be exactly equal. Okay. Okay, and then so the question is, does that mean that population 1 and population 2 have different mean values? Okay. And so, so this time we are creating a confidence interval for the quantity mu1 minus mu2. Okay. Minus mu2. Okay. All right, and so and so currently our current best estimate of this value is y bar 1 minus y bar 2. Okay, so what we're trying to do is figure out what is the actual difference between the average or the mean of population 1 and the mean of population 2. And currently our best estimate of what that value is going to be the difference between the mean of sample 1 and the mean of sample 2. Okay? And then, and so this is going to serve as the center of our confidence interval. Okay? So this quantity, so our center, so our confidence interval okay? And then the margin of error that we have will depend on the amount of variance that exists for this this estimate. Okay. So we will have, and so I'm just going to tell you what our standard error is. Okay, the standard error is going to be we're into, okay, and so you can kind of think of this as we've got like a little right triangle. And then so on one side we'll have standard error 1, which is and then over here we have SE2. And then so if you think of, just Pythagorean's relationship, it's this squared plus this squared, and then you take the square root of that. And so so this squared is this, and this squared is this, and then you add those two together, and you take the square root, and you get this thing right here. Okay. And so our resulting confidence interval will be y bar 1 minus y bar 2. This quantity goes in the center, plus or minus our critical value t star times the standard error, which is going to be okay. So let's just try out a simple example here. Okay, so we could say, is there a difference between the mean height of men and the mean height of women? Okay, and so we're going to we will make a confidence interval for the difference between means. Okay, so so I'm just going to arbitrarily label sample 1. Sample 1 will be the men, and then sample 2 will be women. Okay, and so let's say I've picked a random sample of 15 men. The mean height of these 15 men we'll say was 69.5 inches, and the standard deviation of these 15 heights we'll say is 3.1 inches. Okay, and then for the women, let's say we surveyed a sample of 12 women. Y bar 2 we'll say was 64 inches, and the standard deviation for the women was 2.7. Okay. I'm just making up these numbers here. Okay. Here, let me actually slide this over. Okay, so we'll just plug in our values and see what we get. So y bar 1 minus y bar 2 plus or minus t star times the square root of s1 squared over n1 plus s2 squared over n2. Okay, so by y bar 1, 69.5 minus 64. I'm going to just leave t star here for a second. S1 squared is 3.1 squared over 15 plus 2.7 squared over 12. Okay, so our choice of t star again depends on degrees of freedom, and so I'm going to just flip to the next slide and then I'll come back to this slide. So degrees of freedom for a difference. The formula, it's actually kind of complicated, and it's on one of your pages in the textbook, but it's a little too much work involved. So we have a few ways to approximate it. Okay. And then, in our class, we're going to just use this approximation that the degrees of freedom is n1 plus n2 minus 2. Okay? And this is, quote, the generous approximation, in that this number will almost always overestimate the true degrees of freedom. Okay? Other texts will recommend degrees of freedom equal to n minus 1 and using the smaller of n1 and n2 as n. Okay, and this will almost always underestimate. Okay, and so, it's just, does it really matter? It does a little bit. In the when you throw it into a computer, the computer can calculate using the complicated formula to get it, and the truth is that formula itself is an approximation as well, because the true degrees of freedom, it gets really kind of complicated at a theoretical level. So we just leave it and we just say we're going to kind of approximate it, and you could use either of these, and in truth it will almost always be somewhere between these two numbers, and it doesn't really matter. But for our class we will use this. Okay, so for our class. Okay, so with that in mind, how many degrees of freedom approximately will we be using? Yeah, we'll use 25 degrees of freedom, which means our t star is going to be, if I can find the table, for 95% confidence interval. So for 95% confidence, T star is going to be 2.060, right? Okay. So, so what do I have? 69.5 minus 64. 5.5. Okay, and I'm going to just plug in all of this. 3.1 squared over 15 plus 2.7 squared. I'm going to take the square of that. 1. I'm going to multiply this by 2.060. 2.31. Okay, is this okay with everybody so far? Okay, and so if I, let me copy this over. So 5.5 minus 2.3 is 3.2. 2, and then we'll try plus 7.8. Okay. And then so remember, this was sample 1 represented, sample 1 was men's heights, and sample 2 were women's heights. Okay, and this is the interval for mu1 minus mu2. Okay, so essentially our interpretation will be something like this. I am 95% confident that the mean height of all men is between 3.2 and 7.8 inches taller than the mean height of all women. Okay? Or, you know, if we can accept the idea of the quote average man and the quote average woman, we can say, you know, the quote unquote average man is between 3.2 inches and 7.8 inches taller than the quote average woman. Okay. Of course, if you were to pick any individual man and any individual woman, their height difference could be within this range or outside of this range, okay? Because we're not talking about individuals, we're not even talking about samples, we're talking about the mean of population 1 and the mean of population 2. Okay? And so if somebody asks, do we have evidence that the average height of men is higher than the average height of women, you would say yes. Yes. Okay. I mean that's it's quite clear in this situation, and then so we can say something like we have evidence. Okay, and that's because our entire interval is positive. Okay. Okay. Is that okay?
Just the part where you said we can say that because our entire interval is positive. If it were negative, then what?
Yeah. So let me so I'm gonna just back up a slide here. And then so in this example, I arbitrarily labeled this, sample 1 to be this and sample 2 to be this. Okay. Let's see. What would have happened? What am I doing? Oh, Okay, so if I'd switch these labels, so if this one, if I switch these and I called this one sample 2, and this one was sample 1, what would happen to everything?
Then the overrest is y bar 1 minus y bar 2. That would be y bar 2 minus
So yeah, so this would be y bar 2, 2, and I'm going to just label these all sample 1, okay? So does anything happen?
Yeah, so that part would be negative y bar.
So this part, I would have to switch these, right?
Yeah.
Okay. I mean, does this change at all, though? No, that part remains the same, okay? So this will be 64 minus 69.5, but everything else really remains the same, right? Okay, so then the only change here is I'm going to have a negative 5.5 and a negative. So are we in agreement that this is really the only thing that would happen? Okay? Okay, and so so in this case, my interval is now negative 7.8 to negative 2 point, what is it? Well, let me see. Negative 5.5. I'm sorry, negative 3.2. Okay. All right, and then so now sample 1 is the women and sample 2 is the men. And so my interpretation, if we had to contrast this to the other page, it would be something like, I am 95% confident that the average height of women is between 3.2 inches and 7.8 inches shorter or lower than the average height of men. Okay? But that's effectively saying this exact same thing, right? So changing arbitrarily, the label of which group is sample 1 and which group is sample 2 is arbitrary, and it doesn't really matter. You might get, your interval will just end up being the negative of the other interval, okay? So however you say it. And then so it's either going to be, and if you're going off of the strict interpretation of mentioning sample 1 versus sample 2, it would be, in one case we're saying, I'm confident that women are this much shorter than men. And in the other example I'm saying, I'm confident that men are this much taller than women, okay? But effectively, that's saying the same thing, okay? Yeah.
Just to be sure, so would it be incorrect then if I had, I mean, just in terms of convention, if I had the prior situation where the sample 1 was men, and I was like, oh, you know, I'm 95% confident that the average height of women is lower, da-da-da-da.
No, that's not wrong.
It wouldn't be
It's not wrong. It's not, like, if you did it this way and then you, I mean, I don't know. I don't, you know, I'm not super nitpicky about stuff like that, okay?
Just wanted to-
Yeah, I don't know. Because it's negative, it would be, you know, conventional to say whatever group 1 is shorter than group 2.
Okay.
But if you want to just say group 2 is taller than group 1, that's fine, okay? As long as you're labeling these things correctly and you're saying, you know, in comparison 1 is this much more or less than the other, that's fine, okay? So really the labels of these groups are don't really matter, okay? Okay, and in this case, our entire interval is negative, okay? So we would say we have evidence that that the mean height of women is lower than the mean height of men. Okay. All right. And then okay. So we have that. In other cases, okay, so let me back up. So if we look at the difference between y bar 1 and y bar 2, we have a difference of basically 5.5 inches, okay? And when we create the confidence interval around 5.5 inches, our entire interval remains either entirely positive or entirely negative, okay? And so we would say this difference of 5.5 inches is statistically significant because it is statistically significant, it is significantly different from 0 in that the confidence interval does not cross 0, okay? So for the heights of men and women, mean difference between the samples basically 5.5 inches. Okay, and then after creating the interval, the confidence interval, that mean difference, the intervals did not cross 0. So we say this, so the observed difference of 5.5 inches is what we call statistically significant. Okay. On the other hand, if let's say instead of measuring heights, we measured IQs. Okay, so we took men and we took women, and then we measured their IQs. So we had sample 1. We'll just call the men again, and then sample 2 will be our women. Okay, and then we measured, you know, Y bar 1, Y bar 2, and these are IQ scores this time. Okay, so let's say you go through the work. Of just plugging in numbers, okay? And then your resulting interval for mu1 minus mu2 is, you know, -3 to +5. Okay? And then so here the interpretation would be I'm 95% confident that the mean IQ of men is between 3 points lower and 5 points higher than the mean IQ of women. Effectively, we are saying we do not have a statistically significant difference between the average IQs of men and women. Okay, so because this interval crosses 0, so I don't know, let's say or something like that. So because this interval crosses 0, okay, we do not have evidence that the mean IQs are different. Okay, or in other words, 0 is a plausible value for the difference in mean IQs. Okay, and so here, you know, our random samples, whatever they were, in our random sample, we might have gotten an average IQ of 101 for the men and an average IQ of 100 for the women. Okay, so we are observing a 1-point difference between the averages. But is that 1-point difference significant? when we create the confidence interval, the resulting confidence interval crosses 0, so we say that 1 point difference is not statistically significant. Okay, so so the observed difference of 1 point is not statistically significant. Okay, is that all right? Yes, question.
Are there any rules people follow for choosing what T star they want to use? How confident they want to be about it?
I guess it just depends on how you're feeling. I would say 95% is a pretty common value. That's just kind of convention, like, I don't know, probably because we have 5 fingers on our hand that we said 95%. That's good enough for me. But you know, if you want 94 or 96 or 99, people use that. But I would say 95% is kind of the.
Do people just try and get as big as they can and like avoid 0? So, and, like if we go up to like 90, for the previous example, we probably go like higher, like 96, 97, but then the interval gets bigger, then you won't get 0. Is that a thing?
I don't think so. Yeah. So we're going to talk about hypothesis testing in a moment here. And you know, similarly, we use an alpha level of 5%, and this is kind of this arbitrary thing that has come to be accepted, and it probably should be somewhere around 5%, but there's nothing magical about 5% in of itself. And then, you know, confidence intervals, probably 95% is a good level to choose, but it's probably something, it should be something around there, and not necessarily that 95% is a magic number that does something. Why don't we take a little break here, and then we'll talk more.